Welcome to the Electronic Security Networking Technician Webinar Training, section number 9. The Electronic Security Networking Technician Training and Certification Program is an in-depth training and testing program aimed at electronic security technicians and personnel, people who would install IP cameras, IP access control, IP-enabled physical security devices onto local networks and the Internet. The ESNT program is administered by the ETA, the Electronic Technicians Association. To complete and receive your ESNT certification, you must complete all 9 sections of the webinar training, and this is number 9 or the last one. And you also must attend a one-day hands-on networking lab where the written certification test is also administered. You can check our website, SlaytonSolutionsLTD.com, for certification classes and testing dates in your regional area. My name is Dave Ingebrigtsen. I'm your trainer today. I am ESNT training. I am a certified fiber optic trainer. I am Network Plus certified. I've been in the electronic security business for 33 years. For the last 12 years, I've been running Slayton Solutions, which is a training company that provides vendor-independent networking and fiber optic training for the physical security business. This webinar is webinar number 9, and we are going to be talking about common network testing, how to test, and when we have problems with network connectivity, how can we test things out both on the local network and on the Internet. We're going to cover that stuff today in this webinar. So first we're going to talk about what can be a very common problem, and that's power problems. Computers, and when we say computers now, our IP cameras and our access control panels are also computers now. You know, our door locks, anything we're hooking up to the network. These devices can be affected by power problems, just like everything else. But one of the things that you need to be aware of is that a power sag is when we have a downward drop of voltage or drop of AC power. That's called a sag, and sags can be particularly damaging and dangerous to PC equipment, cameras, etc. So if we have an upward spike in the power, it's called a surge, and a downward drop would be called a sag, and an extended power sag would be called a brownout. And of course, you know what a blackout is. That's when you have no power at all. Now, it's very possible that if a device has locked up, you know, it has quit functioning due to some kind of power problem, it may need to be reset, have the power removed and then reapplied before it'll, you know, come back to normal. This is one of the reasons that in an earlier webinar we talked about power over Ethernet and how important, how useful it is. Well, another reason it's useful is that if we get our power from a central location, either through a PoE-enabled switch or a PoE midspan hub, and if that device is powered by a UPS, an uninterruptible power supply, well, we're going to get clean power. That's important. And we're going to get some battery backup in the event of total power failure. So UPS power is a good thing. PoE is a good thing for us when we're looking at potential power problems down the road after devices have been initially installed. Now, all of our devices, virtually all of them, have some kind of LEDs on them that indicate that they're plugged in and they're connected to the network and they are communicating. If you've plugged it in, powered it up, and it's got a light and the light's not lit or blinking, well, there's something going on and it's not good. So what you obviously the first place you look when you have what appears to be a dead device is look at the lights. There's no lights, there's no power, there's no connection. Now, one thing to watch for on a network switch is a rapidly blinking light on a device that just constantly blinking, even though the device itself may not be transmitting any video or you know, access control information, whatever information it transmits. It's not transmitting information at the time, but it's putting something on the network. This is what we call a chattering NIC card. This is where the NIC technology in the device is having a problem. It's locked up and it's just constantly throwing random packets out. This is something that can occur, and this is something you need to watch for when you're in the troubleshooting process. Now, when we look at where we're going to have problems with our devices, a lot of those problems are going to center around the simple things. the cabling and the connectors. Remember, you're going to have a cabling tester for your Cat5e, your Cat6, Cat7, your copper cable. That tester is going to be a two-ended tester. It can be an inexpensive one, 80 bucks or so, US, or you can spend more money if you want to. But it's going to be a two-ended tester, and here's the important point. Always test every single cable, jumpers included, every cable you're going to use to connect your devices, whether you built the cable or whether somebody else terminated the cable. Everybody makes mistakes, and often our mistakes are in the cables themselves. So you got to test every one. And along with your tester, you need jumper cables to connect this tester into the jack on the wall or to connect the other end into the patch panel. Make sure your jumper cables are good ones, and make sure you've got spares. What can often happen with jumper cables that are constantly used is a little spring clip on the RJ45 plug will lose its springing capability, making it loosen the socket so it keeps sliding back out. That's bad. Always have good jumper cables with you, and always have spare ones. They're inexpensive. Always have spare jumper cables. Now, one of our friends, when we're trying to find a cable in a bundle of cables, is the tone generator. Many of the testers that are available have a built-in tone generator. It puts a tone on the cable we're testing, and then we can use the probe on the other end to find the cable out of a bundle of cables or something like that. So remember to have a tone generator available that'll connect up to a Cat5e copper cable so that you can find it, or possibly hook up to a coax, whatever, so it generates a tone and you can find that cable in that bundle of other cables. Now, when we test fiber optics, it's a little bit different. We've really got three ways to test a fiber. The first way to test a fiber is a flashlight. A standard flashlight, doesn't matter what kind of flashlight it is, it could be a big one or a small one. Standard flashlight will go through 4,000 feet of fiber if the fiber is not broken somewhere along the path, and if the connectors aren't broken, and if the splices aren't broken. If the light comes through at the other end, you know the fiber is not broken. The flashlight is a no-go test. If the light doesn't go through, that fiber is not good. Now, if we want a quantitative analysis to test how good a fiber is, then we need to use what's called an OLTS, or an optical loss test set. It consists of two components, a light source and a meter. And what you're going to have is a light source, and we'll see it on the next slide, where we have a light source on the left-hand side, and you see mine here is, as illustrated, can be set to 850 or 1300. It's currently set at 850. The power's on. It's got an ST connector on the top, and it's got a jumper cable that comes down to an SC, Sam Charlie connector. This is an example of a hybrid test lead. If you're doing fiber optics, you're going to have to be able to test both the STs, the Sam Toms, and the SCs, the Sam Charlies. So if you have hybrid jumper cables like I have, you're ready to test either one. But this illustrates the SC connection. And then over here on the right-hand side, we've got our power meter. Now this power meter reads in what's called dBm, or decibels reference to 1 milliwatt of light power. 1 milliwatt of light power is 0 dBm. Negative 3 dBm would be a half a milliwatt. And when we get down to negative 30 dBm, which you see illustrated here, that is 1,000th of a milliwatt of light power is coming through from the light source to the meter. Now, let me just point out that this meter set you're seeing here is pretty old school. It's about 8 or 10 years old. Nowadays, a modern meter set, there would be a 0 button on the power meter on the right-hand side. And once you have hooked up your test leads to make sure they're good, and then you would press the 0 button, and what the reading would be on the right-hand side would be 0 dBm, or pardon me, 0 dB. Now you're going to read decibels of loss. So when you hook it up, as you see in this drawing here, you could see how many dB of loss is there in your test cable, and it's going to show up on your power meter. And this is standardized. The losses in fiber optics are standardized based on the number of connectors you have the number of splices you have, and the length of the cable. A connector set should have no more than 3/4 of a dB of loss. A splice, mechanical or fusion, should have no more than 3/10 of a dB of loss. And if, for example, we're testing 850 nanometers, as we are in this drawing, in this picture here, 850 nanometer multimode fiber is going to lose basically its 3.5 dB of loss for every kilometer of fiber, or roughly 3,000 feet. You're going to lose half the signal in a multimode fiber. But all these losses in fiber optics are standardized, and when you look at an optical a fiber optic setup where you're going to use a transmitter and receiver, you look at the specification sheets for those products, it's going to tell you these products can take -12, -13 dB of loss from the transmitter to the receiver. So this is how you measure that to make sure that the fiber you installed, or the fiber that you're being allowed to use by the customer, is at least within it's within industry specifications, or there's not too much loss in the cable for the devices that you're going to connect. So here you see we've got a fiber optic transmitter, and here we're reading the light power coming out of the transmitter, and you see we're reading -16.5 dBm. So fiber optic troubleshooting can be a very simple process. If you have a fiber optic link that you hooked up and it was working 3 months ago and now suddenly it's not working, the first place you go is to the transmitter. And you do what I'm doing right here on the screen. You plug your power meter into the transmitter with the transmitter powered up, and you say how much light power is the transmitter putting out. And then you look at the spec sheet of the transmitter, and it'll say this transmitter puts out somewhere between -15 and -17 dBm of light power. Okay, fine. This thing is within spec. It's putting out -16.5. It's putting out less than a milliwatt of light, but it's within specification. So then you would go to the other end, to the receiver end, and you would plug the you reconnect the fiber that's hooked up to this transmitter. You'd go to the receiver end, and you would read how much light power is coming to the receiver. And the receiver will have a spec sheet that says this receiver must see from -15 to -20 dBm of light power. If that amount of light power is reaching the receiver, then you know the receiver is getting enough light. So what's defective? The receiver's defective because it's getting enough light, but it's not working properly. So fiber optics can be very, very simple to troubleshoot. Go to the transmitter first, check the power output, reconnect the fiber that's hooked up to it, go to the other end, check the power that's hitting the receiver, and if it's not if there's not enough light coming out of the transmitter's bad. If there's enough light hitting the receiver, then the receiver's bad, right? Logically, it's pretty simple to consider. Now, there is another type of tester. Our optical loss test set gives us a measurement of the quality of a fiber optic link. There's another type of tester called an OTDR, or optical time domain reflectometer. Now, what an OTDR does is it gives you a picture of a fiber. The problem with the optical loss test set, as illustrated here, is it can tell you the quality of the fiber link, but if there is a problem, it can't tell you where the problem is. Well, the OTDR, properly hooked up and used in the proper manner, can tell you where a problem is, and these problems, or where we have optical loss, are called events. So this is a situation that's outside the norm. It could be a connector set, it could be a fusion splice or mechanical splice. We could have excessive loss over the fiber length, or we could have a bend radius violation in the fiber. Any of these can create a loss event, and those loss events will be illustrated on your OTDR. Some OTDRs printed on paper, some OTDRs do like the one you see illustrated here, where it gives you a computer screen. Now, this is what a typical OTDR trace would look like, and we've got two axes that we're dealing with. One on the bottom is the distance from the OTDR, because you're going to connect the cable under test up to the OTDR, usually by using a box called a build-out box, which has known good fiber in it, so that you sort of the same situation we had with the optical loss test set, where we want to isolate our cable under test from our tester itself. You typically would use a build-out box, but what you get in an OTDR trace is what you see here. And if we look over here on the left and start checking it out, the first thing you're going to see in an OTDR trace is a big hump, and this is called the dead zone. OTDRs use lasers only, whether it's a multi-mode or single-mode OTDR. And the laser signal, when it's pulsing out of the OTDR, the first thing it hits is it hits the connector end that's plugged into the OTDR itself. This gives us reflection, and that reflection creates what we call this initial dead zone, this initial hump that you see over on the left-hand side. Then that curls down and comes into a flat area, and we call this the backscatter area. This is where we start to read good information about our fiber cable. If we see a sharp angle up and down, this is indicative of either a connector set or a mechanical splice. Whenever we have a connector set or mechanical splice, we will have what's called a reflective event. The light energy, the laser light energy, is going through the connector set. There's going to be some reflection back. It's called the Fresnel effect. It happens, it's a physical property. There's nothing that can change it. So when we have a connector set, we will see this hump up or this spike up, and that tells us it's a connector or a mechanical splice. Now further down the line, you see where it takes a dipping down. This is going to be indicative of a fusion splice or possibly a bend radius issue where the fiber is excessively bent. And then at the end of the fiber, we're going to see, again, a reflective event, because that's where the fiber ends. And then over here on the far right-hand side, where it's bouncing around, we call that the noise floor. Different OTDRs can be set up different ways to do different things, but this is basically the kind of picture you're going to get. And it's going to tell you where your connector sets are. It's going to give you the distance from the OTDR. It's going to give you the distance in cable feet. It's not going to give you the distance as the crow flies or the distance it takes you to walk to get there. You know, it's going to tell you in cable feet the distance to the connector set is this, the distance to the fusion splice is this. So OTDRs are very helpful, particularly for outside plant or big fiber installations where the fibers go a long distance and you want to be able to test them out. And certainly if you have an OTDR handy, the smart thing to do after you have hooked up a fiber link and it's working is to shoot it with the OTDR and retain that image, store it electronically or store a printed copy of it, so that if there's a problem later, you can hook the OTDR up again and you can shoot the fiber again and see if maybe somehow the fiber has been cut or damaged in the process, that it has changed from when it was good, it has changed now and it's not working properly. We can do that if we store our OTDR traces either electronically or we store printed copies of them. So now we're going to switch off of fiber, and we're going to talk about our basic troubleshooting that we can do from Windows to start testing out various devices on our network. And the thing that you need to do is know how to get to your command line in Windows. And to do that, I'm going to show you first here how to do it. You click the Start command, you click the Run command, right here you type CMD, Charlie Mary David, and you click OK, and now you get this black box. This black box is your command line. And to those of us who are old school guys, it's the DOS prompt. It's got the C and the colon and the slash and the directories and stuff like that. It's the way computers used to be before we had Windows. But it's from this command here that you're going to do a lot of the testing stuff that I'm going to show you here in the next few minutes. So remember how to get to the command line, and it's available in Windows 7, it's available in Windows Vista, it's available in Windows XP, it's available in every version of Windows that there's been. So know how to get to the command line on your particular computer. Understand I'm using Windows XP, so that's how I get to it. From what I just showed you is how you get there with Windows XP. Now, the first thing you do when you're getting ready to do some troubleshooting is you need to know about the PC netbook, laptop that you are using. You got to start there, and you got to say, what's going on with my PC? And to do that, we go to ipconfig. So we go into our command line, we type ipconfig, and it gives us our Windows IP configuration, and it gives us the IP address is 192.168.1.102, gives us the subnet mask, gives us the default gateway. And it also tells us it's an Ethernet adapter, so it's a wired Ethernet connection. It's got an IP address, it's got a subnet mask, and it's got a default gateway. You have to know where your laptop is first, or your netbook, or your desktop, if that's what you're using. You got to start there and say, what's my IP address? Because chances are you may have to change your IP address in your laptop to be able to communicate to devices on your customer's network or on a different network. So ipconfig gives you that. Now, there's another option called ipconfig space/all. The space is important. You can type it in all caps. You can type it in lowercase. Doesn't matter. But remember that space and which way the slash is going. This gives you more details about the configuration of the PC that you're testing. So here you see illustrated an ipconfig space/all response when I did it to my computer. And you see down here under Ethernet adapter, it tells us, first of all, it tells us who made my NIC card. It's National Semiconductor. Tells me the physical address. Remember, that's the MAC address, or that's also called the Ethernet address. So it gives us that information. DHCP enabled. Yes, what does that mean? It means my computer got a DHCP address. When it was turned on, it got it from the DHCP server. It gives me the IP address. It gives me the subnet mask. It gives me the default gateway, the DHCP server, and the DNS server. Notice that the DHCP server, the DNS server, and the default gateway are all the same address, 192.168.1.1. Nowadays, in modern networks with the modern internet, all of our DHCP requests and our DNS requests go to the default gateway, and then the default gateway, if it has to go to a DNS server, it goes to the DNS server out on the internet, or actually goes to the internet service provider, who then goes to the DNS server, who then passes the information back to you when you are trying to resolve an address like www.google.com into its numeric address. And remember that on the internet, the real address is the numeric address. The URLs we use, google.com, espn.com, SlaytonSolutionsLtd.com, those are universal resource locators. Those are names, but those aren't addresses. They are associated with a numeric address. Notice also here at the bottom, we get our lease time. So we know that this thing has leased. It was done, October 8th, 2008, and the lease expires on October 11th. So it's a 3-day lease or something like that. So ipconfig space/all gives us more information than we will get with just ipconfig. You can do either one. But what's important for you to remember here is that this only tells you about the computer you did it to. It doesn't tell you about any other computers or devices on the network. It only tells you about the computer you're sitting at. Okay. Now, probably the most basic and the tool that's used the most in networking over the local network and in some cases over the internet is the ping command. Some call it packet internet groper. There's other acronyms for it, but basically what the ping command does is it sends out a number of packets at a set byte length, and it asks for a response. And if the device is on the network, it will respond and say, I am here, I'm responding to your ping. So it's the screwdriver of network testing. Just like you use your screwdriver all the time, when you're installing an alarm system, you're going to use ping all the time to make sure devices are on the network and to test out their IP address and their response capabilities. Now, most all devices on a local network will typically respond to a ping. There's some circumstances where in bigger enterprise level networks, sometimes the IT people will turn off ping response on like their main servers and things like that. So that's something to consider. But Ping almost always works on the local network, but sometimes it doesn't work on the internet. Some devices on the internet are set. Some people set their networks on the internet to not respond to a ping command. Why would they do that? Because hackers use software, which is, later on in our live lab, we're going to show you how to use a software called Nmap. And Nmap you can scan thousands of IP addresses in a couple of hours. And hackers will scan blocks of thousands of IP addresses, and they're looking for a response. If they get a response on a random IP address, well, then they know there's a machine there, right? The machine responded to the ping command. So in some cases, some people will turn off ping response over the internet. Doesn't mean their network doesn't work on the internet. It doesn't mean they don't have connectivity. They just don't respond to the ping. But what ping does do, the standard ping command sends out 4 packets, asks for a response for each, and it tells the operator that the device is present and how long it took for the packet to round trip to the target. So, to the target and back. What does a good ping look like? It looks like what we've got here. You see here where I pinged 192.168.2.75. It sent out 4 packets, 32 bytes long. You see the response time is less than 1 millisecond. And it's also got a TTL of 255, and we're going to talk about the TTL a little bit later. But we did get a response for every single packet sent out, and it's less than 1 millisecond, which on a wired network is what we expect. So we know that that device is there on the network and it's responding. Simple enough. If we do pinging to a Wi-Fi device, it works the same way, except the response times are going to be a little bit longer. In this case, you see the first response took 14 milliseconds because it had to go through the Wi-Fi access point, had to get to the device, and then we start to see quicker responses of 3 milliseconds. And what you're looking for here, when you're doing testing on a local network at least, what you're looking for is a consistency of the response time and a consistency of response. You should always get a response on the local network, unless by some odd circumstance that device has had its ping response turned off, which happens very rarely on a local network. Now, what does a bad ping look like? Here I pinged an IP address 192.168.2.18. It sent out 4 packets, and I got 4 requests timed out. What does that mean? It means that my computer sent out the packets, it waited a certain amount of time, it didn't get a response, and it said, hey, you know what? I ain't getting a response, so request timed out. This tells us something. That address that we just pinged is not active on the network. There is no device on the network right now that is using that IP address. So if we do get that kind of response to a ping, why did we get it? Well, it could be that you just fat-fingered the target address. You didn't put the right target address in of the device you're trying to hit. A corollary to that is that you may have programmed the device, let's say it's an IP camera, and you think that you programmed it as 192.168.2.50, but you actually programmed 192.168.2.55. That's going to give you that kind of result. You're not hitting the right target, right? You're not hitting the right IP address, so it's not going to respond. Now, the third one on the screen, hey, if the device isn't connected to the network or it isn't powered up, it is not going to respond to the ping test. Now, the last one is the fourth one is a little tricky in that just when we're in a situation in an enterprise network where we've got a building, let's say it's a big building, and they've got 200 people and they got 200 computers, they're not going to have one local network in that building for all 200 computers, even though they could, because we can have up to 254 individually addressed devices on a Class C network. But chances are they subdivided their networks using VLANs or separate switches or subnetting. They did something to make their networks smaller and to provide security for their networks. You don't want the sales guys getting into the accounting guys' computers and back and vice versa. So the point here is you've got a DVR in an office. It's plugged into a jack on the wall. You're trying to ping the DVR from Tony's computer, which is, on the other side of the office, on the other side of the room, and you try to ping it, and it won't ping, but you know you programmed it right, what's your problem? Well, maybe Tony's computer, even though it's in the same room, isn't on the same local network as what you've got your DVR plugged into. So how would you figure out whether Tony's computer is on the same network or not? You would IP config Tony's computer. And if your DVR is on 192.168.2, let's say it's 192.168.2.50, and you IP config Tony's computer and he's 192.168.3.30, well, guess what? 192.168.3 will not talk to 192.168.2. They just will not communicate with each other. This would be an example of where we've got our testing PC not being programmed to the same network as the target. We also have some issues with some higher-end switches where they've got access control lists that can control which machines can talk to certain devices on the network, so that could give us an issue as well. Now, there are variations to the ping command that can be very useful for our testing purposes. Earlier in this webinar series, you learned that Ethernet packets can be longer and shorter. Well, when we use a ping command with a -L, the letter L, this allows us to change the length of the ping packet. So we can test our connection, our round-trip connection, from the testing computer to, let's say, an IP camera. We can do it with big packets to make sure those big packets can pass all the way through the network. Why would we want to do that? Because with our IP cameras and video encoders, they make really big packets, usually, for the video images themselves. They'll make maximum length packets, like 1,514 bytes long. So what we might want to do is the test that you see here at the bottom. Ping space -L space 1500, how big I want the packet to be, and then I'm testing 192.168.1.10. I type that into the command line, and now I'm going to get where it does a ping. It sends a ping packet of 1,500 bytes, and if those come through cleanly and I get good responses, then I know that my path from the testing computer to the device I'm testing is good for those large packets that a video encoder or IP camera might be producing. Now, another variation of ping that you can use, and it's very handy, is called ping-t or ping space -t. Now, what the normal ping command does is when you type ping, it sends out 4 packets. If you type ping space -t and then the IP address or the URL you want to go to, what that's going to do is it's going to continuously ping until you turn it off. And this is an excellent tool to use for resolving connectivity issues. You're trying to hook up a camera, you can't figure out quite what's going on, you're wiggling some wires, you're doing this and that. If you have launched a ping-t test, one technician could be sitting at the computer watching the ping-t test, and then when when connectivity is restored and that device is hooked up, suddenly it'll quit saying request timed out. It'll say it's hooking up, it's hooking up, it's hooking up. So now we know that the device is functional. So remember that you go ping-t, and then if you want to end it, you do it with the Control-C function. So let's go and try one of these. So we'll go here and we'll say ping space -t, 1- and 192.168.1.10. And now you see here, it took 47 milliseconds to get there the first time, and now you see I'm getting a couple of weird ones there. One at 73, one at 80, one at 45. Now this would be indicative of, we're getting some kind of interesting performance from our network switch here. It seems like every 4th or 5th packet is coming out with a pretty high number. This would indicate a switch that's very busy, and I am using very low-end switches here. So this could be part of our issue. But you see what's happening here. When we do our ping-t test, it just continues to ping. And normally you would want to do this test for at least 60 seconds. Now, one of the things that's happening here, I believe, is that this camera is also transmitting, this is one of my cameras, so it's transmitting video all the time. If we go Control C and end it, and now if I go to, by the way, I can hold down the F1 key and it fills it all back in. If I do just the 192.168.1, which is my router, you'll notice here now, between my computer and my router, I'm getting a very consistent, less than 1 millisecond communication round trip, and that's what I expect to see there. Okay, so remember, ping-T, let it run for a minute, then do Control C, and you get your statistics. Your statistics tell you that in this case we sent 19 packets and we received 19. We lost 0 packets, and that's what we expect to see in a local area network. Notice here that our average came out on the top one, the first one we did. We lost 0 packets, but our average was 18 milliseconds. That's way too high in a local network. So there's something going on in my network at this moment that's causing that variation. Now, another feature or another test you can do is called traceroute. But to explain traceroute, first we need to go back up to here. Look at these packets, the reply packets we got in our ping test of the wireless device. And notice that they've got a TTL. The TTL is called the time to live. In this case, the TTL is 255. What does that do? Well, when a data packet is initially made, it has a TTL, or time to live, of usually 255. When it gets to the first router that it comes to, that router looks at the TTL and says, okay, 255. Then when it retransmits the packet to the next router, it ratchets down the TTL to 254. And when that gets to the second router on the internet, that router is going to take it from 254 and take it down to 253 and transmit it to the next router. And so the packet, the TTL, will continue to drop by an increment of 1 as it goes through every router, and then that keeps going on until the packet has a TTL of 1. When it has a TTL of 1, the router will kill the packet and send a response to whatever device generated the packet on the internet and say, I'm router number, here's my IP address, I killed your packet at 12:15 on June 6th because it had a TTL of 1. Why do data packets have a time to live? Data packets have a time to live so that packets don't endlessly wander the internet looking for home. If a data packet goes through 255 routers and can't get to where it's supposed to go, it ain't going to get there. So it needs to die, and it's the TTL that tells it when it tells the router when to kill it. The reason I explain this to you is this is the way that traceroute works. What traceroute does is, and you'll see it, we'll do one where it's trace RT. But what traceroute does is it starts off, it's similar to ping in that it's looking for responses, but it starts off sending 3 packets with a TTL of 1. So those packets are going to go to the first router. That router is going to kill the packet and send the reports. Then it sends out 3 packets with a TTL of 2. Those get through the first router and they get killed at the second router. Then it sends 3 packets with a TTL of 3, which gets it through the first 2 routers, gets it to the third one. Traceroute will test out to 30 routers, and it's used typically over the internet to see what kind of connectivity we have. So we can go to our command line here, and let's go down here, and let's do a traceroute, and we'll do it live, and we will go to a website in Germany, and we will start trace routing. And you'll see here the first router that shows up is the router that is my my Linksys box. The second one is my DSL adapter at 172.16.0.1. And then you're going to see the complete path that we take to get from, in this case, downtown Chicago to Germany. And we're going to get there. And you see that it's telling us each router that it's going through. At some point, we're going to get to Deutschland. The .de is Deutschland, so that's Germany. And here you go. So this gives us, and let's pop it out so you can see the whole thing. This gives us our information about all the routers we went through, and it gives us all of our response times. Now what you're looking for here is some level of consistency of the numbers. Now traceroute can be beneficial because it can tell you where a signal stops on the internet. But one of the issues we have, and something we need to understand, is that there is nobody that owns the internet. There is not one company. There's the Internet Assigned Numbers Authority who issues IP addresses. But besides that, you know, there's all these different players on the internet and all this different connectivity that's supervised by different companies. So you could be having a problem if you're trying to get from Chicago to Germany. You could be having a problem in England, or a problem in France, or a problem in Germany, or a problem in New York City, and it could be not your internet service provider. It could be one of the backhaul carriers. It can be hard to, what I'm getting to is you can see the problem on traceroute, but that doesn't mean you can fix the problem, because you know, we don't necessarily have a lot of pull with, you know, some internet service provider in Germany. Now, another test you've got, or another thing that you can get out of the command line, is your address resolution protocol, or your ARP table. When your computer wants to connect to another computer on the local network, when you go to Internet Explorer and you type in the IP address of you know, your router or of a printer on your computer, you don't type in the MAC address, do you? You type in the IP address. And you know that your computer then sends out a broadcast command. In this case, the Hannah's computer is trying to reach 10.1.1.2, so it sends out that broadcast packet, and the machine that has that address sends back the response. Well, those responses are stored in what's called the ARP table, and they're only kept for a short period of time. They're kept usually as long as that communication is current. Now you can go to your ARP table in your command line by going to your command line and typing in ARP space -A, and it tells us this, at the time I did this, my computer, its IP address is 1.102, and it knows about a device at 1.1 and 1.101. It knows the MAC, or physical addresses, and notice over here that the type says dynamic. By dynamic, that means that my computer went out and found, through the broadcast discovery process, it went out and found these these IP addresses, or the MAC addresses to go with these IP addresses. So remember that if you need to know who your computer's been talking to recently, you could go to the ARP table and take a look. It's really not super useful for us, but it is a function that's available in your command line. Another one is called NSLOOKUP. NSLOOKUP gives you the ability to type in NSLOOKUP for www.slaytonsolutionsLtd.com, and it comes up with an address. It gives us a numeric address, 68.178.254.135. Now, understand something here. The SlaytonSolutionsLtd.com address, that's where my website is at GoDaddy. That's not the IP address of my house, right? That's the IP address of my website. And here's how you can get a URL, and then you can resolve to its IP address with NSLOOKUP. Now, NetStat gives us the ability to see what ports are open on our computer and what they're doing right now. So you see that we have our active connections. It tells you the protocol. It tells you the local port numbers that are in use. It tells you the foreign or local host addresses that are in use, or the IP addresses. And it tells you if it's established, it's listening, that sort of thing. I have never found great value in NetStat, but it is a test, or it is information that you can pull out of your computer through these command line functions. Now, we can test on the internet. We always can figure out who our customer's internet service provider is by going to DNSstuff.com. Very simple to do. We can go here and say, I can go to Internet Explorer, and I can say, okay, if I go in this example, if I go to DNSstuff.com, And you see right here, it tells me what my IP address, 99.140.168, come on, there. And I can control copy that. Then I can go to my tools, and I can go into who is. I have to move this over just a little bit. I can go to who is, which is down here, and I can enter that IP address. And I can type free, click the free button. You gotta love the free button. And it's going to come up and tell us that this internet service provider is coming from where? Query is ambiguous. The query is assumed to be. Well, something came up. I didn't do something right. Let's hold on for a second. Let's back it up. And let's go to IP who is. 99.140.168.138. Try it one more time. Well, here's what we'll do instead. Let's put in my website. And we click the free button, and now it's going to tell us who's registered for that domain name, Slayton Solutions Ltd. It's registered at Address Creations, and down here you see my address information. We can put in an IP address, or we can put in a website URL, and it's going to come up in DNS stuff. And that's a real important website for you to remember, because it gives us all this information. And that's that whois command. You can go to whois.net. There is a number of places on the internet that perform the whois query for you. Now, IP whois, you see here, which is what I just showed you, how you can do it with a URL, or you can do it with an IP address. If you want to know the IP address, the public IP address at your home or at your customer's location, all you got to do is go to Internet Explorer, and in the address line type www.whatismyip.com, and it's going to come up and give us an IP address. From there, we can use that IP address, and we can find out who that internet service provider is. Now, another feature that comes with some products is called Mac Search software. Some cameras, access panels, NVRs, DVRs will come with a CD-ROM disk. And if you put that disk in a PC on the network and you connect that device to the network, it will find the device by its MAC address. And then you can set basic settings such as the IP address you want, the local IP address you want it to have, subnet mask, default gateway, and port numbers. You can set that stuff up through the software. This is kind of nice because you could hang 10 cameras on the network. You wouldn't even have to program them. The Mac Search software would find them all, and then you could put IP addresses in all of them. Keep in mind, you need to know which MAC address is on which camera and where they're located in the building, or else it could get a little tricky and a little confusing. Now, there is other types of software like network discovery software, like we're seeing here, Interview. And what Interview can do, and this is a very powerful tool, what Interview can do is it can give you the capability to live monitor your customer's network. And you see all the things that have come up on this particular test network where a foreign device is trying to gain access and then disconnected. You lost a wireless connection. You've got a bandwidth problem between two of your switches. You've got a duplicated IP address. You've lost SNMP communication. This is a service, it's a software that you can put on one of the computers on the network. It actually monitors that network and keeps it, and when there's issues and problems, it delivers live emails, instant messages, it enunciates the alarm condition. So this is something that we're going to see more and more of in the future. When we're connecting our physical security devices up to these networks, we're going to want to be able to monitor the whole network, and Interview software will do that for you. Now, we're going to talk about network transport issues because it's real important that we understand the three things that we're testing for when we want to see the quality of a local network or the quality of the internet. The things we test for are the latency, the packet loss, and the available bandwidth. Now, latency is pretty simple to understand. How long does it take a data packet to get from point A to point B on a network? And In our local wired network, we should see latency of 5 milliseconds or less, where if it's wireless, if it's a Wi-Fi device, we might see latency of 10 milliseconds or less. But it doesn't matter how big the building is, and it doesn't matter how many network switches we're going through. In our local network, we should see 5 milliseconds or less of latency. If it's longer than that, there is some kind of issue. Now, over the internet, we will see latency, often see latency of more than half a second, 500 milliseconds. Long latency can cause problems for some of our IP cameras and encoders, particularly if they're transmitting in JPEG or motion JPEG, where they're transmitting in TCP and we're looking for receipts. If the receipts don't come back fast enough, the transmitting camera or video encoder or whatever might just break the communication. They'll say that, this isn't working. I'm not getting responses fast enough. So that's what latency is about. And packet loss is just what it sounds like. If we have a stream of data packets, how many of them get lost? When we're on a local network, we should have no packet loss, 0. On the internet, we're commonly going to have packet loss up to 5%, and that's typically what happens. So we can go to a ping-t test here, and we can say I'm going to ping-t to Germany, and here you're seeing that it's taking half a second in some cases or more to round trip from Chicago to Germany, right? Now, we can let this run for a while. Sometimes when I do this live, you would see some packet loss. Sometimes you don't, okay? Understand that internet quality varies during the time of day and having to do with how it's working at that particular time. Internet quality is not a static thing. Internet quality can be better or worse at various times. So you see here we're not suffering any packet loss, but we are seeing pretty long latency between here and Germany. And you also notice that the time to live is 46. So we're going through a bunch of routers to get there and back. So I'm going to Control-C to end this. And you see that our average time is 502 milliseconds, or half a millisecond, to get from Chicago to Germany. So the ping-t test tests for both latency and packet loss. Now, when we're looking at network transport issues, we think about the available bandwidth. We've already discussed how in our local network we've got a lot of bandwidth, and our bandwidth is really limited, assuming our cable and connectors are good. Our bandwidth is limited by the throughput of the network switches, but our internet connections are going to be much, much smaller than our local area connections. So where you're going to see issues is on the internet, and that's where you're going to want to do an internet speed test. So here you'll see where we're going to go to a website called myspeed.visualware, and let's see, I got to get this out of my way so I can see where I'm going. I'm here, and I'm in Chicago, and now it's going to come up, and it's going to say I want to do my test. Maybe. Okay, so I click to start the test, and now we are live testing my DSL adapter here, and we're going to get an uplink and a downlink connectivity. So I've got a download speed of 747 kilobits per second, and now it's going to look for the upload speed. We hope. Couldn't figure out the upload speed, and it says my quality of service is 33%. Now here where they talk about quality of service, they're saying that 33%, that means packet loss. And what we're looking at there is a 67% packet loss, primarily, I believe, because this upload speed test didn't function. But you're going to want to use this test to give you the uplink and downlink of what your customer's connection is. And what's going to be important if you're doing video is the uplink command, or pardon me, the uplink test. Because if you're pushing video up through the internet, you want to see that uplink test. So let me try this one more time just to see if we can make it work. Let's try this one, Pittsburgh. Maybe Pittsburgh will work better for me. And notice it gives you in the chart, it shows you what a typical DSL would be, what a typical satellite connection would be, that sort of thing. Notice here we're getting a different number than the test we did before when we went to Pittsburgh. Here we got 563 kilobits. The last one was 700 something kilobits, correct? And now we still seem to be having some issue with the uplink test here. It doesn't want to do it for some reason. Normally it does. Nope, there you go. My upload speed is 112 kilobits. So do you see the asymmetrical nature of my DSL connection? Bigger download, smaller upload. And remember, if we're hooking up video, it's that upload speed that we have to look at. So this is what the test you do on your customer's network on their internet connection to see what kind of bandwidth they have. By the way, you can go to my website, and there is, on the first page of my website, there's a place where you can download a questionnaire sheet that gives you this information so that when you're at the customer's location and you're talking to them about putting in IP cameras or other IP-enabled devices, it asks the questions that you need the answers for so that you can know what to do when you get out there and do the actual installation. Now, when we're doing our network troubleshooting, always remember to check our power, our cables, and our Ethernet connectivity. It's the simple things, ladies and gentlemen, that cause us the most problems. It's the things that are obvious that we overlook. Look at the power, look at the cables, and look at the Ethernet connectivity and make sure it's there for you. Your laptop itself, you have to enable and turn on the NIC card in your laptop. You may be using your laptop always as a wireless device, and let's talk about how we do that. We go to the Start command, and we go to we go to the Control Panel. We go to Network and Internet Connections. Then we go to Network Connections, and right here you see that my local area net connection is connected, and I don't have a wireless connection here on my desktop computer, right? But if this was your netbook or laptop, you'd have a wireless connection. Maybe your wireless connection is turned on and your local connection is turned off. If you're looking at something, you want to turn it on or off, all you do is right-click it, and it's either going to be disabled or enabled. While we're here, we might as well talk about how you change the IP address on your wired NIC card, because you're going to have to be able to do this. The way to do that is to right-click it, then go to Properties. And from here, you go to TCP/IP, Internet Protocol. You click Properties. Right here, it'll say Obtain an IP address automatically. So my computer, my desktop is getting a DHCP address. But I could say use the following IP address. And right here, I could type in 192.168.1.50. And then it'll automatically fills in the Class C subnet mask, and I could put in my default gateway if I want to. Now I'm going to cancel out of this because I don't want to end this webinar prematurely. But this is the way that you set the IP address in your netbook or laptop so that you can talk directly to that camera, directly to that NVR, or put it on your customer's network, giving your netbook or laptop a static IP address. You need to know how to do this, and you got to be comfortable with it because you're going to be doing it all the time, okay? And I will give you one clue here, is that I've seen many times where I've changed the IP address in my computer, but it doesn't take the change. What you need to do is you need to right-click here, and where it says disable, I'm not going to click it, but you would click that to disable the card, and then you would right-click it again to enable the card. Toggle your network card. Toggling your network card will force it to take the new IP address. I'm not going to change my IP address because I don't want to lose this webinar. But that's the way you change your IP address. Now, one of the things you can do, and you should know how to do, is how do you test your own PC to make sure that it is that the NIC card is working. And the way you do that is you go to the ping command and you ping 127.0.0.1. This performs a loopback test to make sure that the NIC in your computer is working properly. The third thing when we're thinking about network troubleshooting is, and I just showed you by how you set your IP address, is our computer on the right network to communicate with the other devices? Remember, if the network is 192.168.2 and your computer is 192.168.1, it doesn't matter what you do. Your computer is never going to talk to those devices on that network. So be aware of that. Now, if everything's checked out so far and you still can't reach that device that you think you should be able to, well, you should ping a known good address on the network. What would be a known good address? Well, that would be typically your default gateway address, the router. Ping the router. It should respond. If it responds, then we look at the device we're trying to reach, that camera or access control panel, and say, well, it must not have the IP address in it that I think it did, or I changed the port number. Remember those software port numbers, the TCP IP port numbers. If you change a camera off of port 80 and you make it port 8562, well, that's fine. You will always have to use that port number. Now, when you ping the IP address, the camera should respond to the ping. But remember, when you're pinging an IP address, not a port number. If you find that you can ping it, but you can't reach it through Internet Explorer, you have forgotten to use the port number that you put into the device. Or, in last case circumstances, there's a possibility that the device has failed. Now, what are some of our common problems and solutions? Common problems are miswired jacks, jacks that are sloppy and are falling out of their connections, broken wires, wires being flexed too much. We can have IP addressing issues. Anything you did wrong is going to make it so it doesn't work right. In your IP address, your subnet mask, your default gateway, and your port numbers. It's also possible in the enterprise level network that you could have some issues with the switch programming. And you may have to work with the IT people, make sure that the female sockets on the switch that you're plugging into are active, that they're turned on. Maybe that's something the IT person has to do for you. Now you notice down here at the bottom I've got bad equipment ? The manufacturers in our business uniformly build good equipment. Very rarely, unless we misapplied power and we made the smoke come out of the box, very rarely does the equipment fail. You should know how to default your device back to its factory settings. If the light's light, chances are the equipment is not defective. So if we've got problems with our IP addressing, go to the device directly. Bypass the network and plug your netbook or laptop directly into the device and confirm the IP address settings in it. Be prepared to default the device back to its factory presets. If you've somehow lost it, you don't know what port number you put into it, you don't know what IP address you put into it, you can default it and start over. And often that will solve your problem. You just start over and get it fixed. If you've got network connectivity issues, we can isolate the device, verify its IP settings, then start investigating the switch and router settings for proper VLANs, ports, and protocols. And this gets us into that enterprise level where we're going to have to work with the IT person to say, how come my device is hooked up? I know it's got the right IP address in it, but it won't communicate over the network. What do you think the problem is? Oh, it's going through switch number 4. Oh, yeah. Okay, well, here, let me check that out. Oh, I see what I did. Okay, here, let me fix that. That's the kind of thing that you can run into, and it's going to be an IT person issue to solve it, okay? Now, I already mentioned that chances of the equipment being bad are pretty slim, but it can happen. Remember that if your device link lights are active, chances are the device is okay. We could have a chattering NIC card or a bad NIC in a device. Very rare, but it can happen. And always be prepared to reset your device to its factory defaults and start over if that's what you have to do. And then you should be able to get that device up and functional on the network. Now this is the end of Section 9 of the webinar training for the ESNT Electronic Security Networking Technician program presented by Slayton Solutions Ltd. There are training and reference manuals that are available for you to read and study prior to coming to the one-day hands-on lab and taking the certification test. They are the Technician's Guide to Networking Security Systems and the Technician's Guide to Networking for Security Systems Enterprise Solutions. These books are available at ADI. They're also available at our website, www.slaytonsolutionsLtd.com. Now, if you have your ESNT study guide, and this may be where you are watching these webinars right now off of a disk, in that study guide there are the webinar sections, there are the PDFs of the webinars, and there's a quiz for each section that you should take, and you can secure your future in the physical security business with ESNT training and certification program through Slayton Solutions Ltd. and the ETA. And I thank you for watching this webinar today.